So we already know what is the definition of vector space. So let us recall it quickly. So what is a vector space? A vector space, which we will call linear space in this course. Linear space means basically it is a vector space. We denote it by X over field K. So K is either the set of real numbers or the set of complex numbers, right? So X is a vector space over R or C if it is a non-empty set with two operations. So the first operation is plus. So whatever first operation is that is a map from it is a binary operation. Binary operation means it is a map from X cross X. So X is this given set. X is this given set. So plus is a map from X cross X to X defined by X comma Y to X plus Y, right? So this first operation we call addition, and the second operation so that also we know that is a scalar multiplication. So that is a map from K cross X to X, and it is defined by this way, right? So this is a scalar multiplication, and this operates these both operations satisfy certain axioms. So the axioms are quite standard. So there are 8 axioms. First axiom is that for every x and y in X, we have x plus y is y plus x. So that is called commutativity with respect to addition. Then we have associativity. Then we have existence of zero element in the set, so that x plus 0 is x equals to 0 plus x. Then for each x, there exists negative element. So that x plus minus x is equals to 0 element is equals to minus x plus x. Right. So all the real numbers, complex numbers, Rn, Cn satisfy these properties. Then the other properties are with respect to the scalar product. So 1 into x is x. Then we have associativity. For every scalar k1 and k2, and x is in x. So if you have doubts, you can ask in between. Anyway, this is elementary things. But still, if you have any doubt, you may stop by and ask the question. So this is distributive laws. There are two distributive laws. First one is this one, and second one is k1 plus k2x is k1x plus k2x. Every k1 k2 in k, x is in x. Okay, so the these 8 axioms are satisfied, then only then we say that X is a vector space over K, where K is either a set of real numbers or set of complex numbers. If X is a vector space over R, then we call it a real vector space. Otherwise, we call it a complex vector space. So, what are the examples of vector spaces? Yes, so you can tell whatever example you remember.
R over Q.
R over Q is a vector space. Yes. What is the dimension?
Infinite dimensional.
How it is infinite dimensional?
For finite, we can take C over R.
Yeah, but my question was different. Why it is infinite dimensional? So what you said is correct, that it is a infinite dimensional, but
I don't recall, sir, but no, sir. Sorry, sir. I don't recall that. But Sujito sir has given this question in our linear algebra paper. I
yes.
forget the
So
proof.
yeah, proof is basically that there are infinite number of irrational numbers. So that gives you infinitely many polynomials which does not have uh, yeah, you cannot write as a irrational number, you cannot write as a linear combination of rational. Is it correct? That is the proof or what? So first example is x equals to r and k is equals to q, right? But why we are taking here only two fields, r and c? Because r and c are complete. That means in that we have all the Cauchy sequence converges. But if you take k equals to q, then this is a field which is not complete. So that means we do not have Cauchy sequence converges. And in function analysis, we will discussing what I mentioned, Banach species, in which we have every Cauchy sequence converges. So that is a complete nonlinear space. So therefore, one of the reason is that we will not take examples which has k equals to q. Okay, anyway, but this question is interesting. Just check that why the dimension is infinite. Dimension of r over q is infinite. So just check this. Even I don't remember what is the exact proof of this. But what are the other standard examples?
The
So
set of all continuous function.
set of all continuous functions. So continuous functions where
The field is of real numbers.
field is a real number. Okay. So let us start with some basic examples. So first example we all know is that Rn and Cn So if we take X equals to Rn, then it is a field we will take R. Same example is C, and then field we will take is C. These are the standard n-dimensional examples. Here also we can take K is R, but we will not go in such examples because mostly we will consider it as a complex vector space, standard in the standard notation. So this is one example. The next example which we know is a matrices. Right, we'll come to the continuous function, but let me write down in the order which I have written. So here also when we discuss matrices, we need to mention whether it is over R or C. Right, so let's say it is a complex matrices, and we take K to be the set of all complex number. So this is a so when we say it is a vector space, we need to mention the vector space operations also, right? So here it is simple, so we are not writing, but what will be the operations here for matrices? If it have two matrices A and B of order n cross m, then how do we define A plus B and this one? So A plus B is the matrix whose ith entry is ith entry of A plus ith entry of B. Right, this is the way we define the matrix addition. Similarly, matrix scalar multiplication is defined as A times Aij. So these are the addition and scalar multiplication in matrices. Now, the next example is a set of functions, let us say. So before going to the continuous function, we just consider the set of functions which are defined from S to K. What is S? S is some non-empty set. Right. So if you take this as a X is a set of all functions from a non-empty set, fixed set S to K, where K is either real number or complex number. So in this case, how do we define addition? So these are the functions. So that means we need to fix some element of S. So what will be this f plus gx? That is defined as pointwise addition, right? So that is fx plus gx. Similarly, so here we are taking for every f and g in x. Similarly, what is k times f? K of x. So this way we can define continuous the addition and scalar multiplication. And what will be the negative element here? So just we need to substitute k. K is -1, so that means we'll get minus f of x. Right, so that will give us f plus minus f, that is a 0. And what is 0 here? 0 means what? Zero element of this vector space is a not a zero number. It is a zero function, right? So here 0 means 0 is a map from S to K defined by zero, and on X is 0 element for every X in S. So basically it is a function. So we can call it either 0 or some function, let's say G. So where G is defining this one. So this is a 0 element. So this is exactly the similar example of continuous functions. Let us come to the last example, that is a set of continuous functions, but we can't say just it is a continuous function. We need to consider it from continuous function from where to where, right? So let us define it on some non-empty set S, where S is whose interval 0 to 1, right? So what is this set? This set is the set of all continuous scalar value. Scalar valued means either real valued or complex valued functions defined on closed interval 0, 1. Okay. So X set we define. Now the operations are here also we define operations similarly. So addition and scalar multiplication we will define pointwise. Right? And what? So this is a fifth example. Now last example we want to discuss, which is a subspace of this space. So let us consider the functions f from k to k such that f is defined as c0 plus c1x plus up to n x power n, where n is non-negative integer. So what is this set? Basically, we are taking the functions which are of the form c0 plus c1x plus cn x power n, and moreover we can say that c0, c1, these are the constants. So if we have this type of function, what is it called? That is a polynomial, right? So we are basically taking x is the set of all polynomials with coefficients from the field K. Okay. Now what is the dimension of? So first of all, what is the addition and scalar multiplication here? Is it a vector space? Set of all polynomials. Is it a vector space?
Yes, sir.
So what will be the operation corresponding of addition and scalar multiplication in this case? Polynomials are also continuous functions, right? So can we take the same operations?
Yes, sir.
right? So the operations are same, point-wise addition and scalar multiplication. So for example, if we have the first polynomial is a0 plus a1x en x power n, then second one we have b0 plus bm x power m, then addition we can define as f plus g x is so for simplicity we can assume m is greater than n, right? So the other case is also same. If m is less than n, also we can define this. So in this case we get a0 plus b0 plus a1 plus b1x up to the smaller is n, so an plus bn x power n. Then after that there will n is smaller, so there is no terms. So the next terms will be bn plus 1 x power n plus 1, and the last term will be bm x power n. So this is addition. So basically it is just fx plus gx itself, and the same way kfx is also defined as k times fx, just k multiplied to the polynomial f. So operations are defined point-wise addition, point-wise scalar multiplication, right? So now what is the dimension of this vector space?
No, yes, sir, it's finite dimensional.
So what is the dimension?
M plus 1.
M plus 1. So again I'm explaining this set. I'm not taking n
Sir,
dimensional
it is
polynomial.
infinite dimensional because
Yes,
the degree of the polynomial is not defined. We are taking all polynomials.
polynomial. Yeah, so that is what I'm explaining, that we are taking all n, all possible n. So we are taking polynomials of all degree basically in this set of all polynomials of all degree. So what you said is correct. If we take only n-dimensional up to n-dimensional polynomials, then dimension is n plus 1. So that is right. But in this example, we are taking all the polynomials. So that means we are taking nth degree polynomial also, n plus 1th degree polynomials also, and so on. So now that means the degree is infinite, right? That is our guess. So how to prove it? So proving that degree is infinite, let us start with degree is finite. Dimension is finite. Right? We are discussing dimension. So how do we find basis in a vector space? So suppose we have R3 and we are R3 over R. Yeah. So how do we find basis of R3? What is the process? So we know the dimension of R3 is 3, right? Because it has 3 elements in the basis. So how do we find basis elements? 3 elements.
We have to take three vectors which are linearly independent, and none of them is can be written as the linear combination of the other.
Exactly. So that is the next step. What I'm asking is that first of all, basis definition. So dimension is 3 means its basis has 3 elements, right? So it has a basis with 3 elements. Now how to find these 3 elements? We want to find a basis of R3 which has 3 elements. So what is that basis? What are the 3 elements?
One zero 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 1 0 and 0 0 1.
So these are standard basis. So how did you find this? So you just now explained this also in your answer. So what do? Is we take, first of all, we choose some non-zero vector, right? So if you take non-zero vector, then that means 1 0 0 is Li subset of R3. Then what is our goal? We need to find 3 elements. So that means what we do? We add one by one elements in this set and we make it complete basis. So that means, so first thing is, there are 2 criteria in basis. The first thing is it is Li set, but this set is not basis. Why it is not basis? Because its span of this set is not R3, right? So now span is not R3. So that means I can add one vector from R3 which is not in this span, right? So that is, we can choose this one or this one. Both of them are not in R3. So we get a new set which having 2 elements. So again, this is a Li, and span of this set is also not R3, right? Why it is span is not R3? Because we already know that this vector is not there, right? It belongs to R3, but 0 0 1 we cannot write as a linear combination of these elements, these 2 elements. So then finally now we get a set which has these 3 elements. This is Li and its span is R3. Right. So this is a process. So like Gram-Schmidt orthogonality process, this is also a process to finding a basis. So whenever we get span exactly equals to the vector space, we get a basis, and until we get a vector which is outside span, we can add that vector and we can enlarge the Li set. So this is regarding R3. This we already know. What about this set? So in this set, what we will start? We will start with the simplest element, that is 1, right? So the singleton set 1 is Li. Of course, span of 1 is not this set X. X means the set of all polynomials. Right. So now, which element of X is not span of single one? So the next one is, next power of X is X. X is not in the span of 1. Right. So that means we can add X in this set. We get a new set, which is again Li. Right. span of 1x is not x. Why? Because x square we cannot write as a linear combination of these two elements, right? Because left side x square is that, right side there is no power of x. So there is no k1, k2 satisfying this property. So therefore span is not x. So now next what we'll do, therefore we can add, therefore x square is not in the span of 1 comma x. So that means one by one we are adding the element and we are enlarging the Li set. In general, for every natural number n, x power n plus 1 is not in the span of 1 x up to x power n. So this we can prove by mathematical induction, right? Because up to 2 we already proved, to 2 elements, for n elements we'll get this. So now this says what? This says that for every n, this set will not span the whole set. So therefore the dimension is infinite. Right? So same thing we can do in this example of Q over R. So we can add one by one the irrational numbers. Right? So we can start with 1 and then 5, E, so on. So there are infinitely many irrational numbers. So therefore the dimension is infinite. So basically in this course we are going to study infinite dimensional vector spaces, and moreover we will study the continuous functions and linear functions over those spaces, right? So I'm not writing all this definition, linear combination, span, all these things, basis. So those things you already know, right? Now let us go to some elementary set theory. We will also require some set theory here. So if we have a function f from x to the set of real numbers or complex number, then we will define the conjugate function So of course, in this case, we are taking k equals to c. Where k is equals to set of complex number, then we are defining conjugate function, which is defined as f conjugate x, which is fx conjugate for every x in capital X. So, like complex number, we can define complex conjugate. We can define complex conjugate for the complex valued function, and we will define a range. Also, we know the range is the set of all values which fx assumes, and then 1 onto function. So let us discuss some. Let us recall some countability axioms. So a set is called finite if there exists a function f from, so the set x is finite if there is a function x2, the set 1 to up to n, which is bijective. So bijective means it is a 1 1 and 1 2 function, right? So this is regarding finite set. The same way we can define the enumerable set. So set x is called the enumerable if there exists a function f from x to set of natural number which is bijection, and set x is called countable if it is either finite set or it is a denumerable. So denumerable means sometimes it is known as countably infinite set, right? And last is a set is not countable, then it is called uncountable. So this is regarding countability. Now we know how to define the union and intersection for a finite collection. So we will also need the collection which is infinite. So if E alpha is a collection of sets, then whenever we define intersection of E alpha, what, so each E alpha sets E alpha which is a subset of some universal set. Let us call E alpha is subset of U for every alpha. We are taking E alphas. So what is the intersection of E alpha? Intersection of E alpha is, we know that it is a elements in the universal set such that x belongs to E alpha for every alpha in A, right? This way we define intersection of A and B, right? A and B is what? X belongs to the universal set such that either x is in A or x is in and x is in B because intersection. And similarly we define union. So here we write or. So here we have two sets. But now if we have infinitely many sets, then also we can define in a similar way. So intersection means in each set x belongs. Right? X belongs to E alpha for every set E alpha. Similarly, union is defined as those elements of the universal set such that x is in E alpha for some alpha in A. Right. So this way we can define the arbitrary union and intersection. So the question is that let En be the set so En be a family of countable sets. That means each EI is countable. So the question is the this infinite union n is equals to 1 to infinity is the set a countable set. Okay, so you can try this question. Let me stop today's lecture here.